No. How
the
does
side, on the side there. Yeah.
First, of course, the problems that typically interest or where MDL technique is supposed to be of help is seen if we write estimation or modeling problems in this sort of three-level hierarchy. That like here 1, 2, and 3. But if we have a fixed structure or model structure and fixed number of parameters, then and we only want the optimal parameter values, then of course we have a relatively easy problem. This is a traditional problem about which much research and much results have been produced over the decades. But then as soon as we just take one step higher and start asking for the optimal number of parameters, then all of a sudden the theory breaks apart. And I quite flatly say that there are only, or have been, only ad hoc criteria, and when you think about that, you will have to agree. Where is the theory that would allow you to answer these kinds of estimation problems? And they, of course, are just another estimation problem, nothing fundamentally different from the first. And then if we take one more step higher, that we suddenly start comparing completely different and arbitrarily chosen model classes, then I must say that there are no traditional solutions. In fact, this is not even contemplated in a serious way. And further up there I have this, this is a foil that I did not make for this occasion. I just took a bunch of foils along for this trip, and I'm in all desperation just picking something here. So some of these statements are needlessly sharp, but nevertheless I'm trying to make the point that you see, in traditional statistics there is no rational basis for comparison of two models, which is kind of amazing when you think about it. That must be one of the fundamental problems of all of statistics. And the key question, of course, is just how to assess performance of a model. And yet, there is a way to deal with these problems in one and the same framework. And the universal performance measure is the code length for the data, and including the model, that any proposed model and model class will permit. And now the question is that what do we mean by a model? What kinds of models are permitted, and what are models in the first place? And again, one can make the rather sweeping statement that all models are probabilistic. I haven't found yet any models that could not be recast in this relatively familiar probabilistic framework. See, these parameters, this k can be anything, or when you start fitting, k might become a function of the sample size and all that. So of course all the parameters that you ever fit must be parametric.
What does x stand for?
X is just some idea. You see, y first is a sequence of y and x is a pair of sequences of observations. You might and you suspect that x might help you in figure. It's like in regression type of situation. Okay. Let me see if I can find some. Maybe I'll find another foil that will try to put this in a nutshell. Let me show a few of these. My forthcoming talk in Uppsala. Then I'll get my act a little better together. So here is okay, we again have data. This time I don't have this pair y given x, it doesn't matter. The ideas or the approaches are just the same. Of course, its old idea, fundamental idea in statistics is that you would like to find a reduction map, a map that will reduce the data into something, a handful of parameters, statistic. And you would like moreover that map, that statistic be such that the data that gave rise to this handful of parameters would be random. And if that were the case, then that map would have all the useful information about the observed data, be sufficient statistic. Now, but there is this word random. So what does that mean? Well, we borrow from the algorithmic theory of complexity. Measure of randomness would be a code length. And then the next foil, we would then indeed have an ideal situation that for some number of parameters and for some statistic, that induced density function that you get on the set of data that gave rise to this parameter, that if that is independent of the parameter values themselves, you would have would have sufficient statistics at hand. And then of course the code length, the total code length for the data and the sufficient statistics themselves would be minimum if you can encode those estimated parameter values with the shortest code length, because there's nothing you can do about the first part. It has nothing to do with your parameters. Now, the second coding of the parameters will have to be what is known as a prefix code, because you see the code is just a long binary string, and unless you know which portion of that string refers to the coding of the parameters, you would need an extra symbol, a comma, and that's not allowed because you must have a binary string. However, it is possible to do this encoding in a certain way, which means that the code lengths will have to satisfy that inequality known as Kraft inequality. And now you see that this requirement of a prefix coding, which is necessary, automatically gives rise to a distribution on the parameters, whether you like it or not. And it has nothing to do with whether you want to be Bayesian or non-Bayesian. These are just coding theoretic facts. So the so-called prior is nothing but in one-to-one correspondence to a prefix code. So much for the prior. Subjectiveness has no more to do with that than I have to encode certain parameter values. If I know something about them, I'll use that knowledge and do the encoding accordingly. There's no other meaning. And subjectiveness is just that you have the freedom of choosing anything you like. The name of the game is to get the short code length. So there is no difficulty in interpreting probabilities. They are generated by code lengths, whether you like it or not. And it of course has a tremendous power, because you can now forget about some objects of being random and others being deterministic. All objects are something that must be one must be able to describe. If not, then you are in trouble. So, and as soon as you can describe, you can ask logically this question that, well, can I separate the code, the description from the rest? And if yes, as I must, then you are talking about prefix code, and now you are generating a distribution or not. This is simply the philosophical reasoning that gives you this freedom and power that I really can think about all these issues as matters of coding and code lengths. Okay, now we don't generally have this sufficient statistics, so instead we reason in the primitive manner that well, let me use that one of these distributions in the model class, and let me estimate the parameters optimally, and then let me encode the results, except that maximum likelihood estimates in general would have infinitely many binary fractional digits in them. They would be just real numbers. Well, I have to encode them, so I can't permit that. I must truncate them. And then comes the question of, well, how should I truncate them? Well, the principle says that you should truncate them so that the total code length becomes the shortest. And that leads automatically to this precision optimization problem, and you get this MDL criterion. Asymptotically, that code length for the parameters becomes the k over 2 log n, but non-asymptotically not. And these days there is a great interest in applying the criteria on neural networks. And there the asymptotic version definitely is too gross, because you tend to have parameters in the order of 1,000 or thousands, and you may have maybe 10,000, 100,000 observations. So there's absolutely no justification for the asymptotics. Nevertheless, this same principle must apply, and the issue is that how to work out a formula which is valid even when the asymptotics are not justified, and it of course can be done. However, there is an inherent weakness in this two-part coding business, and the weakness is that using that just the distribution that you got from the model class, just using that isn't quite right, because if I normalize it the way indicated, I would get a bigger density or probability for the data, and of course its negative logarithm should be shorter. You can also see this in another way, that you have redundancy here. You have many codes for each x, because every parameter value will give one possible code. And if the name of the game is to encode just the data, then it means that I'm wasting nodes in this huge code tree. One node for x, each x is needed, and nevertheless I have the three repeating nodes, any number, as many times as I have parameters. So there is obviously some sort of redundancy involved. If I kick out and utilize those nodes for encoding other data sequences, everybody would get a shorter code length. So that's another way to see the effects of that. This density is smaller than the one that you should be using. But of course, to find this normalizing thing is difficult. However, there is a general way to, this business simply, here I illustrate that every parameter value gives me actually a code for the for a given data sequence. So there is a general way of removing redundancies in such situations, and very general way is simply that I raise 2 to the negative power of lengths of all the possible codings for x. And you see what happens that I'm getting a distribution on x alone, and that will be, its negative logarithm will be a code length for something that is non-redundant. But all this actually now leads into something quite familiar. Namely that we should work out this sort of work out the predictive, the Bayesians call it predictive distribution, and take its negative logarithm as the stochastic complexity, which is nothing but the shortest code length for the data sequence X given the model class. I call that shortest thing stochastic complexity. In this, let me take back. And yeah, I wish I had other foils available. With those, I would have shown that a neat parallelism or how to generalize this famous theorem of Shannon's, but I don't have those foils, so I won't go into that. I'm just flatly here declaring that by you applying that redundancy removal technique, which amounts to working out the predictive distribution, I'm flatly suggesting that the negative logarithm of that will indeed give the shortest code length. And that I call stochastic complexity. Now, you can now show indeed, for many, many cases, that asymptotically you can't beat this code length, no matter how you would do the coding with the given suggested model class. There simply is no way, so that the stochastic complexity name indeed is justified. Here I'm saying that oftentimes we have an integral, and of course it imposes a restriction, because I would have to evaluate it. So we are getting these familiar conjugated priors model classes where we can actually work out the integral, and we have nuisance parameters, and now in this Bayesian ML2 technique it has been suggested that you should maximize the predictive density, which amounts to the same thing, that you would minimize the stochastic complexity with respect to the nuisance parameters. But of course, and this is well known, that it leads into trouble in certain situations, especially when you have suggested a prior which is very difficult to describe, something that these epsilon contaminated priors are a good example. So that the MDL principle says that it's not that you should minimize, but you should minimize the stochastic complexity plus the code length needed to describe that prior itself. It's just the old same game again. And when you do that, I claim you never run into trouble. Because if somebody suggests a very tricky prior which is tailored to the data, it's going to take the same order of code length to describe that prior than to describe the data. And such priors simply won't be optimal. They will be kicked out in this competition. And you would avoid these anomalies. Okay, I don't want to delve too deep into this nor spend too much time. let me show a few theorems. If we have this is a generalization of Shannon's coding theorem. But here we have a smooth parametric class of densities. What smoothness means, I don't need to go into here. There are reasonable conditions. Then this theorem says that asymptotically the best way of, these two results, I and double I. First, the double I says that there exists a density which is as good as any data generating density you can pick in the model class. And this density of course has no parameters itself. It is simply a universal density. It learns whatever data generating density you pick here, whatever theta you pick, this other one will learn it sooner or later and achieve the shortest code length. And indeed it is shortest because the first part says that no matter what you pick, the Kullback-Leibler distance divided by k over 2 log n cannot be smaller than unity, except in a small set, vanishing set. You must have an escape clause, because if I pick g of x equals your data generating density, then of course this could be violated. But there are not too many such exceptions, at least in this measure sense. And if you here pick k equals 0, you would have to reshuffle this a little. You will see that you would have Shannon's or Kullback-Leibler inequality. Now in many, and that was what I intended to originally to talk in this meeting, some of these results that have been proved for AR and ARMA processes, that there exist these optimal densities even of a predictive form which achieve this lower bound. And these sorts of theorems, they would immediately generalize the classical results on least squares techniques and estimators. They would, you would simply apply, instead of the original least squares technique, you would apply it in the predictive form, namely that whatever you estimate is a function of the past. And then you make your prediction and square the prediction error and add it into your criterion, and then at the end of the data you sum up these mistakes you made and you got the predictive squared errors. And if you apply least squares technique that way, you can estimate the number of parameters, fine, and these theorems will prove that your estimators are asymptotically optimal. And estimators now include estimating the number of parameters as well as the parameter values. So these directly generalize the classical optimality results of least squares technique. But they are just tiny special cases of these theorems. Now a totally new chapter. How much time do I have? And indeed, before, let me just flash the final results, and then maybe Matti can sketch briefly and a very interesting and impressive application. Let me just quickly present the results on density estimation. Peter Hall and Ted Hannan a few years ago computed the stochastic complexity for histograms, and here is the result. And when you minimize the number of bins by minimizing the stochastic complexity, you would get that kind of asymptotic optimal rate, n over log n raised to 1/3. and here is the associated estimator. And such an, the philosophy here is that a density estimator is good if it permits a short code length for the observed data, including the estimator that you used. Just the MDL philosophy. And I have advocated that this is the way you should compare any estimators whatsoever. And hence the name of the game is to find an estimator that gives a short code length. And not be too complex to describe itself. And this Peter Hall-Hannon estimator, namely this one, is pretty good. However, you can do much better. And let me show how. Let me show another picture. Here is a set of data, 76 pieces. And here is the best Peter Hall-Hannon kind of estimator with 13 bins. It's the optimum number of bins. That gives the stochastic complexity 577.2 bits for this data set. But you see that it's a kind of nervous estimator. You have very few data points here, and nevertheless the histogram tends to jump up and down as if it didn't quite make up its mind. And if you instead apply the stochastic complexity in the version that you simply add up those various histograms and divide by their number. So you are working out another version of that integral. Then you get a funny estimator. It's really an extended histogram estimator. It has all sorts of bin widths because it's the average of them all. And remarkably, the code length is much better than in the previous case. And you would have to admit that, yes, indeed, you might like this better. It is smoother. It's nicer. It doesn't jump except for these minor wiggles. It doesn't jump nervously. And the point, of course, here is again that any fool can make smooth densities out of histograms, but they are made by subjective means. And in this game, anything that is subjective is to be rejected. It simply is non-scientific, and period. I don't care what you get with those histograms. Unless they are derived by objective principles, forget it. This is not the name. This is not a game of comparing who is more clever in applying these ad hoc principles. Pretty soon it would become a fight who talks loudest and has the most impressive names or something. This is really a humble attempt to eliminate all those aspects from the game, and hence this was a serious problem for us, you see, how to make histograms estimator smooth without, you see, invoking ad hocness. And this seems to be the right answer. All these splines and others, they are valid estimators provided that you describe the estimators themselves and compare the final code length. They might give good results, and then they would be okay. Okay, so much for that. And the theorem says that for this class of densities on the unit interval, the Kullback-Leibler distance, this is now a theorem that generalizes, or there are two theorems actually, that generalizes the original one, the parametric family case, fixed number of parameters, K. So it would say that there is a family of densities describing a random process such that the Kullback-Leibler distance is bounded this way. Instead of k over 2 log n, you will have this kind of n divided by n. You would have a bigger penalty, which is exactly right, because you have a bigger task. You don't have a parametric class, you have a non-parametric class. So the amount of uncertainty in estimating the data generating density will be greater. And this will tell you exactly how much greater it will be. And the second part, or the second theorem, simply says that this indeed is the optimum. It's not in the relatively weak sense that min-max optimum, but this is in a very strong sense that you can't beat the bound except in an essentially vanishing set. And because of you need a little technicalities here, because you can't have measures, non-trivial measures on non-parametric things. However, it's a perfectly satisfactory way of stating what is vanishing. Okay, let me stop here and let Matti spend whatever time he needs to. Yeah, try to just sketch perhaps something. People might. Yeah, exactly. Yeah, and right. Maybe just if you explain the problem and then show the final criterion and then maybe give a results.